All right, friends, this is a redo of lecture 24 because when I posted it, as one of you noticed that the audio was not present. So because I love you, I'm re-recording this particular lecture, and I will upload that in place of the old video. But I'm basing this on the notes I took from that lecture, so what you hear here will be close to what we heard in class. When we last left off, we were talking about a kinetic concept called effective molarity that's very important in chemical biology. The idea is that intramolecular reactions are faster than intermolecular reactions, which is not a new idea, but we're going to use effective molarity to quantify sort of how much faster and why. So here's starting material R, which has both a nucleophile and a leaving group in it, and there's two potential reaction pathways. The reaction of R with itself will be R reacting with another molecule of R with rate constant K1 to give you the linear product, and then starting material R reacting with itself via rate constant K2 to give you the cyclic product. The rate of formation of the linear product with respect to time should be K1 times R squared, and the rate of change of cyclic product should equal K2 times the concentration of R. So let's take the ratio of the linear to the cyclic product appearance. This would be how much slower the linear reaction is than the cyclic reaction. That should equal K1 times R squared divided by K2 times R. And of course, those R's will cancel out. One of those R's on the bottom will cancel out with one on the top, which will give us K1 times R divided by K2. Now at this point, it may be worthwhile to go back and reflect on what the units of these rate constants are. Notice that the rate of a reaction must be in units of molar per second, because you're talking about how the concentration changes with time. If I've got two concentration terms in my rate law, that's going to be in units of molar squared. So in order for the units to work out right over here, the rate constant units have to be in per molar per second for this second order reaction that gives us a linear product. In contrast, here for the reaction that generates cyclic product C, again, the rate of appearance of cyclic product C is going to be in units of molar per second. We have only one R concentration term, so we've got units of molar there. In order to get this right, all we need for our rate constant is for it to be in units of per second. Okay, now let's see whether this works out or not. A ratio should be dimensionless. That means no units. So if K1 is in units of per molar per second, and K2 is in units of per second, and R is in units of molar, all of our units cancel out and we're good to go. Now, there's something else in here that's useful. If we take the ratio of K2 divided by K1, let's look at what that should do in terms of units, right? K2 is in units of per second. K1 is in units of per molar per second. So the ratio of K2 divided by K1 has, units of molar. And we're actually going to define the ratio of K2 to K1 to be called effective molarity, or EM, and that's going to equal K2 divided by K1. And so going back to our ratio, this is going to equal the concentration of starting material R divided by the effective molarity. And now looking at this reaction, notice that when R and effective molarity are equal, the rate ratio should be equal to 1, meaning this rate is the same as that rate. So effective molarity is the concentration that you need to have R at in order to compete with the intramolecular reaction. Another way of thinking of effective molarity is the nucleophile and the electrophile are in the same molecule. How concentrated is the electrophile? How concentrated does the nucleophile feel that the electrophile is when they're covalently attached? If your concentration of starting material is above the effective molarity, then you can get dominance of linear product. If it's below the effective molarity, you can get dominance of a cyclic product. Excuse me, this is important in macrocyclization reactions because in many cases you want the single ring and not the product that comes from multiple linear units coming together. All right, so that said, we need to start thinking about, we need to transition into talking about how to generate predictions for how the rate of a reaction should vary with concentration of starting materials and products and so on, and develop mathematical predictions that we can test experimentally. So the simplest reaction is a first order reaction, and first order reactions are easy. You've probably done this before, so we'll go through it kind of quickly. Starting material A undergoes a unimolecular reaction to convert to product P. The rate of appearance of product P is equal to the opposite of the rate of change of product A. In other words, P only comes from A converting to P, and so the opposite of the rate of change for A should equal the rate of change for P. And the rate law is first order here, meaning it has linear dependence on the concentration of A. So we can use this rate law to answer the question, how does the concentration of A vary with time? To do that, we need to do a little bit of algebra and a little bit of calculus. So I'm going to rearrange this equation to put all of the A concentration terms on one side and all of the other terms on the other side of the equation. So when you do that, you come up with dA divided by dt. I'm sorry, dA divided by the concentration of A equals the opposite of KT. And, oh, goodness. Can I try that again? We take this equation, we put the negative on this side, divide both sides by A, divide both sides by dt. dA over A equals minus K dt. So now we can integrate both sides of this equation from time 0 to time t, and from the concentration of A at time 0 to the concentration of A at time t. When we do that, we get the following equation, which we can simplify even further using property of logarithms. We can rearrange what was written above as just the natural log of the ratio of the concentration of A at time t to the concentration of A at time 0, and that will equal minus kT. We can raise both sides of the equation. We can raise the number e. Since these two numbers are equal, if we raise e to this power, we should get the same number as if we raise the number e to this power. And so that allows us to say that the ratio of A at time t to the concentration of A at time 0 should equal the exponential of, or the number e raised to the minus kT power. And then we'll just multiply both sides by the starting concentration of A to get this integrated rate law. And probably in general chemistry you had to derive that. If you were to plot, this is an equation for something that's called exponential decay. And if you were to plot the concentration of A as a function of time, you would see it start out at concentration A 0, and then you'd see an exponential decay curve that would look something like that. All right. Let's try second order kinetics, which are a little bit more complicated. Second order rate reaction, we'll do one that's a little bit more difficult. You could have two molecules of A reacting with each other to give product P, but let's have A reacts with B to give product P, and there's some rate constant K. The appearance of P with time should be equal to rate constant K times the concentration of A times the concentration of B. Notice that this second order rate constant would need to have units of per molar per second in order for the product rate to have units of molar per second. Okay, and you can use calculus, use integral calculus to write an integrated rate law for this equation. I don't actually know how to do that, but I do know what the answer is, and it's, though you shouldn't memorize the answer, it's a useful enough exercise to show you what it is. So you take the 1 divided by the concentration of B at time 0 minus the concentration of A at time 0 multiplied by the natural log of concentration of A at time 0 times concentration of B at time t divided by the concentration of B at time 0 times the concentration of A at time t. And all of that equals kT. Now, for this to be useful, you'd have to have a way to monitor both the concentration of B at time t and the concentration of A at time t during the course of the reaction, and that's probably unrealistic in most cases. So, what do we do when a situation is too complicated? We try to simplify with assumptions. And we have to hope that our assumptions are good assumptions. So we're going to try to run this reaction under what are called pseudo first order reaction conditions. All right. How do we do this? Well, one way that we can run the reaction under pseudo first order conditions is we can use a large excess of B such that the concentration of B doesn't change during the reaction. In other words, at any time t, the concentration of B is still the concentration of B where we started. How much would you have to use? Well, probably somewhat like 10 or more molecules of B or moles of B for every mole of A. But if you run the reaction under conditions where the concentration of B is constant, then what would happen? Then your rate law could simplify to rate constant times the concentration of A times the concentration of B, but not at B at time t, B at time 0, because the concentration of B doesn't change. And because that's constant, our rate law actually looks like it's only first order in A. The constant concentration of B gets folded into this rate constant. All right, so how would you measure the rate of appearance of product P as a function of concentration of A? Well, you could do you could monitor with time the appearance of, you could monitor the concentration of A as a function of time and get exponential decay curve like this, which you could fit to concentration of A equals concentration of A at time 0 times the exponential of the opposite of KT, only this K is going to be your observed rate constant. Alternatively, what some people do is they will measure just the initial rate. They won't watch the concentration of A as a function of time. They'll run the reaction to only 5 or 10% completion, and in that region where it's only 5 or 10% complete, usually you can find a region that's basically linear, and the slope of that region of change in A with respect to change in T will be pretty close to this rate constant K obs. Then we'll repeat for several different values of B, constant concentration of B. All right, and what would this look like? Well, you would repeat the K obs. You would repeat this analysis to determine a new observed rate constant at different concentrations of B. And then you would plot those observed rate constants as a function of B. And let's assume that you observed that the plot was linear and you fit a curve to it. If the plot of K obs versus B is linear, that means the reaction is first order in B. Okay, so backing up just a little bit, by running the reaction under first order conditions in B, we were able to determine that the reaction is, because it fit this rate law, first order in A. Now we're measuring those observed rate constants as a function of B, and just as we said, if B doesn't change, the rate law simplifies to this, but K obs really equals the second order rate constant times the concentration of B. So if we plot K obs versus the concentration of B, the slope is equal to our second order rate constant K. This works out with our units, right? K needs to be in per molar per second, whereas K obs can just be in per second and A is in molar. K obs in per second here, B in molar, so the slope of K obs versus B will be per second per molar. So those are the correct units. Now, what if we did the experiment and we observed that K obs versus concentration of B is not linear? Suppose, what if it's quadratic? So here's K obs, here's concentrations of B. And what if we see some kind of dependence like this? And let's suppose that we can fit it to k obs equals some constant k times the square of B, concentration of B. This would tell us, oh, the reaction's second order in B. All right? So those are some simple starting cases. But there are a lot of other examples of more complicated reaction mechanisms that we need to be prepared to deal with. So what we're going to do now is we're going to use as an example the SN1 reaction and try to figure out what the rate law for that SN1 reaction should be. Now at this point you might be saying, hold on, I was told that the SN1 reaction of this starting material R, well, let's just call it A to be consistent with what we've done so far, going to reacting with some nucleophile to give the following product and the leaving group Br minus. I was told, product P, nucleophile B, that the rate law for that reaction only depended on the concentration of starting material and not the concentration of nucleophile. So why do we need to even worry about this? And I will tell you that the idea that the SN1 reaction does not depend on the nucleophile concentration is true from a certain point of view, as Obi-Wan Kenobi once said. But I once had a student in undergrad ask me, and maybe you've had this experience too, how can the rate law not involve nucleophile concentration? If the nucleophile concentration is 0, the reaction clearly can't happen, and I agree with you. So this is an oversimplification of the rate law. Let's draw out this reaction mechanism, at least in terms of starting materials and intermediates. Product A reacts in an equilibrium step to give a high energy intermediate I and leaving group Br minus, which we'll call product 1. Okay, and this is an equilibrium step. And it has a forward rate and a reverse rate, and both rates are significant. You can tell that's the case because the high energy intermediate could easily go back to the starting material that does have a bond, right? The carbocationic intermediate is pretty high in energy. Then, in a second step, that carbocationic intermediate I reacts with nucleophile, we'll call it B, with some rate constant K2, and we'll say this reaction is irreversible because the products are so far down in energy from the intermediate energy, carbocationic energy, as to make the reverse reaction impossible, and that gives you product 2. All right, so how are we going to write a rate law for this reaction? Well, if you were going to look at the appearance of product 2, and at this stage, we're not going to make any assumptions about what the rate determining step is. That will come later. For now, we can write that the rate of the appearance of product 2 should be equal to the rate constant K2 times the concentration of intermediate I and the concentration of nucleophile B. But we're not sure what the concentration of intermediate I is, because that's a high energy intermediate and it's difficult to measure, and its concentration is probably low. And it turns out you can show mathematically that if the concentration of I is very small, then the variation in that concentration must also be small. And this leads us to what is called the steady state approximation. That is that during the reaction, for most of the reaction, the rate of change of the intermediate is 0. Its concentration is constant. That's a useful approximation for reasons that I will show you now. If that concentration is constant and the change in that concentration is therefore equal to 0, then all of the ways that we make I or get rid of I must all total to 0. So let's think about all the ways we can make I. We can make it from A, and the rate of appearance of that would be, of I from A would be K1 times the concentration of A, right? How about all the ways we can lose I? Well, we can lose I, or we can lower the I concentration by having I react with product 1 via this K minus 1 rate, the reverse rate constant, to give me A. I'm going to use a negative here because the K minus 1 step decreases the concentration of I. And then the other way I can get rid of intermediate I is for it to react with nucleophile B through this irreversible K2 step. Because this step involves disappearance of I, it will also be negative here, minus K2 times I times B. Now, notice that I have here two terms that have I in them and one term that doesn't. So I'm going to use algebra to get all the terms that have I in them on one side of the equation and all the terms that don't on the other side of the equation. If you'd like to pause now to work the algebra out yourself, you can. I'm just going to write it here, and I'm going to factor the I out. All right. Take a minute to convince yourself that that's true. And then I can actually solve for concentration of intermediate I. It equals K1 times the concentration of A divided by K minus 1 times the concentration of P1 plus K2 times the concentration of B. And then recall that we set up here that our rate law for the appearance of P2 should be K2 times the concentration of I times the concentration of B. Now we're going to substitute all of this in for that concentration of I term. K2 times K1 times the concentration of A times the concentration of B divided by K minus 1 times the concentration of P1 plus K2 times the concentration of B. That is our steady state approximation rate law. Okay. So how does that gel with what you learned earlier about the rate of SN1 reaction only depending on the concentration of the starting material? When is that true? Okay, well, so if the concentration of B is large, or if K2 as a rate constant is much larger than K minus 1, how does our rate law change? Well, then the rate of appearance of product should equal, and the numerator stays the same, but if K2 is much larger than K minus 1, and or if B is much larger than P1, this term dominates the denominator, And we can say that the concentration is basically equal to, or the rate of change is basically equal to this, where we drop the k-1 term entirely. And then look at what that does. That simplifies our equation. B drops out, as does K2, and we're left with a much simplified rate law, which is K1 times A, which is, in fact, what we said and what we were told as undergrads, right? This is the typical SN1 rate law. And what this situation predicts is what are called saturation kinetics. If we were to measure the rate constant if we were to measure the initial rate of a reaction or alternatively, if we were to measure the observed rate constant for this reaction, I'm going to say if we were to measure the initial rate as a function of concentration of B, what we would see is the following situation. We'd have a region where the dependence of the rate is on B is linear, or sort of first order in B. Then we'd have sort of an area where it is still dependent on the concentration of B, but somewhat less than first order. And then out here, it's zero order in B. That is, B is no longer in the rate law. And there's adding more B doesn't get the reaction to go any faster. From a conceptual point of view, this makes sense. If the concentration of my nucleophile is very large, it's going to get to a point where the thing that stops me, the rate determining step, is not this step, but rather the formation of intermediate I. It doesn't matter how much nucleophile I have, because as soon as I forms, it will get snapped up by the nucleophile, and then I'll have to wait again. That's called saturation kinetics. You've saturated the system with B such that adding more B doesn't make the system go any faster. Okay, what are some other predictions? Let's see. Sorry. If the concentration of B is small, then the rate of change of the product as a function of time, in the denominator, the term with B would go away. You'd end up with K minus 1 times the concentration of P1 times K2, K1, A, B, and you'd expect this reaction to be linear in B, or first order in B. And that's what we see in this region of our plot of rate versus B. This is the first order region in B. And then at some intermediate concentrations of B, B matters, but it doesn't totally cancel out the B up here, and so the dependence is somewhat lower than first order in B. Notice an interesting feature of this reaction is the prediction of inhibition of the reaction by product 1. If, as the concentration of product 1 increases, what will that do to the rate of the reaction? That should decrease the rate of the reaction. So one of the ways to test this mechanism is to actually start the reaction with known amounts of added product P and demonstrate that the rate slows down when you add product P. And of course, if product P is large, this term goes, the K2 term goes away, your rate law simplifies to this, and you should see that rate is linear in 1 over the product 1 concentration. And so that can be a way of predicting or probing a reaction mechanism. And again, it makes sense because as we look at this reaction mechanism, if we have a lot of P, that should make the backwards reaction faster and perhaps intercept I as soon as it's formed before it can even find the nucleophile. All right, so we can use the steady state approximation to deal with complicated reaction mechanisms and to generate sensible predictions about what we ought to see in terms of the dependence of reaction rate on concentration, starting materials and products as a function of time, and then test those hypotheses to determine mechanism. All right, I believe that's all we got to in lecture 24. I think we're just a little bit ahead of time, but we'll go ahead and stop here, and I will see you next time.